So now let's go into Module 12.2. In this module here, we're going to discuss design using our Bode plot. So relating back to our textbook, the sections that we're going to be referring to here is section 12.2, which is design using the Bode plot. So a little bit of a refresher, I'm going to cover some more of the topics that we saw in 12.1 again as we tie in the new Bode plot and our method there for the design. So a little refresher on compensators here. Compensators are going to be used in order to obtain desired performance of the system specifications, requirements, here in all three different ways there, but this is going to be what the desired performance of the system is, and we're going to utilize compensators in order to achieve that. We're also going to use these to stabilize unstable systems. So if we test our system and it ends up being unstable, we can use these compensators and different methods of designing these compensators in order to make the system stable again. This explains how much compensation is required to get the desired response. So that's one thing that we're going to be looking at when we're talking about designing a compensator is how much, quantifying it in order to figure out how to put in and what type of compensator to put in. So a quick look here, a little bit of a refresher again from 12.1. We're talking about the fact an open loop might not be good enough, so we're going to need to put in a compensator here. And we're going to use two different methods here. We talked a little bit in section 12.1 about the root locus method. This converts requirements into polar locations on a root locus plot, and we saw how we could use those in order to design our compensator. And this places a 0 and a pole to move the root locus to that point. And that's what we're doing with the compensator is we're going to place that 0 on the pole. And we saw that in our example that we went through. This is also, we discussed a little bit about steady state errors in that as well. So this is all having to do with a root locus plot. But now we're going to focus over here, switch over now to Bode plot. So this here is going to convert requirements into our frequency domain. So that's one of the main difference now is we're dealing with the frequency domain rather than time domain here. So as we're dealing with frequency domain, we have a couple other things that we need to look at here, which is our phase margin, our gain crossover, the bandwidth, our zero frequency magnitude, and our steady state error. So that is when we're going to utilize our Bode plots. So as we take a look at this now, we kind of talked about there being time domain and frequency domain. So we're going to go back up to our basic definition of a compensator. This is any device that is inserted into a system for the purpose of satisfying the requirements or specifications of that system. Now we can break this down a little bit. If we're talking about performance specifications, well, there's three different things that we're going to refer to here. So as we're dealing with performance specifications, we're going to talk about accuracy, so the accuracy of our system, the relative stability, and the speed of response. So these are all things that we need to consider as we're looking at our system for home. What is the most important to us as we're designing a system? Maybe we need a quick response for whatever we're doing. So that's one of the most important things we need to do. So we need to figure out how to design our compensator in order to get and increase that speed of response so it's more close to an instant, like a real-time response. The next thing we're going to look at here, if we're dealing with our time domain, we're going to take a look at our transient state performance specifications, which include our rise time, maximum overshoot, settling time, or damping ratio. So again, as we're thinking about our system at home, are these things that are important to us as far as our specifications go? And then last, we're going to take a look at our frequency domain, and these are the transient state performance specifications there, our phase margin, our gain, and our resonant peak. So now we're going to discuss the design using the Bode plot here. So now we're talking about this in comparison to our root locus plot. There are going to be a couple key advantages to designing a system using this open loop frequency response. So one, the frequency response data are often easier to explain experimentally, which is useful when it's difficult to develop a transfer function model of the plant and actuators for basic principles. So this is, I know a lot of you guys had asked, how do I figure out the transfer function for a system? How do I do all that? Well, if you're doing things experimentally, it might not be the most easy thing to do. So that's why using this plot here and using the frequency data might be a little bit easier for practical application for a system that you're designing hands-on. Number two, the method is also easier to use with dead time elements. And three, finally, this technique is sometimes useful in examining the response and instability of nonlinear systems. So a lot of the systems out there are not going to be perfectly linear systems. They're going to be a nonlinear type of system. And examining the response from that is going to be a lot easier to do using this Bode plot. So we'll continue on with a little bit more of a comparison between the root locus plot and the Bode plots here. So if we're talking about a root locus plot, this is going to be a technique that's going to be used for designing systems within our time domain. So again, the main difference here is time and frequency domain. So if the time domain specifications are given to us or known within the system we're designing or the problem that we're given, then the root locus technique might be good for that. But for our Bode plots, this is something where we're given stuff in the time domain specifications. So if we're dealing with Bode plots, Nyquist plots, or a Nichols chart when we're designing the system here, typically when we're going to be dealing with a time domain specifications of the system. Now, I know we've mentioned a little bit about gain before, but we're going to cover this again because I think it's important here. So gain is to be designed to meet the desired specifications. So you're going to alter your gain in order to meet whatever the desired specifications, requirements of the system are. So if things are a little bit off, you go back and you tweak your gain, or you design your gain at the beginning so that you already get those specifications met. Now, the issue is if we increase this gain, it's going to possibly result in poorly stable or an unstable system. So when that occurs, what we need to do is introduce an additional device or components to alter that behavior in order to tweak it back and meet those desired specifications. So we'll cover down here, take a look, what are some basic type of compensators, things that we can put in line, these devices or additional components to add into the system as compensators. Well, there's electrical compensators, mechanical, hydraulic, and pneumatic, and how you pick these is going to be based upon a couple different things. One, what type of system are you dealing with? Are you dealing with a purely electrical circuit board for like a motor control or something like that? Then maybe you want to talk about an electrical compensator. But also, if you're talking about speed control within a motor controller, maybe mechanical work. Maybe it's a gearing that you can put into the system there to change things. Other types of systems might require that you use a hydraulic or pneumatic. And some other factors to take into account are the weight of the system. So, how much do these weigh compared to what your specifications of your design project are, the cost of these, the size of these, all of those become important when you start picking out and designing a system as a whole for which type of compensator you're going to use for a physical system. So if we talk again, we covered our series compensators in 12.1 here. So we can see this is in line here in series with this here. This is our series compensator. You have your input here and your series compensator right in line with that. And then you can see your feedback loop comes right back around here. So that's going to tell us, make some changes to this compensator here in order to take a look at our desired output and make sure that those requirements or specifications have been met. So we mentioned the Nyquist plots and criteria a little bit earlier. We're going to go into a little bit more depth and a little bit more detail with these, and this is a frequency response analysis technique. So if we talk here about the Nyquist stability theorem, we can recall that a plot of the frequency transfer function, our t, j omega here, in vector form is the polar plot, and we can see down here plotted is the location of the tip of the vector as our omega varies right here from 0 to infinity. So we can take a look at the figure below here, and this is our frequency response of a stable linear system here, and we can see that on the axis of the plot are the real and imaginary parts of our frequency transfer function. Now the thing to notice here is that the angle and magnitude of that frequency transfer function are represented on the same plot. But when we're talking about our Bode plots, the magnitude and angle each have their own plot versus log. So a little bit more history and background on Nyquist plots. So these were invented by an employee at Bell Laboratories, Nyquist, which is the premier technical organization in the U.S. at that time. Now, these plots are going to be a way for us to show frequency responses of linear systems. Now, there's several different ways of displaying frequency response data, and these include, or are not limited to, the Bode plots and our Nyquist plots here. So comparing those two now, the Bode plots are going to use frequency as the horizontal axis and use two separate plots. So we just briefly discussed earlier to display the amplitude and the phase of the frequency response. And sometimes it's important to look at those separately. You can vary them for different desired outputs or different requirements of your systems. Now, whereas our Nyquist plots are going to display both amplitude and phase on a single plot using frequency as a parameter in the plot. So our Nyquist plots are going to have properties that allow us to see whether a system is stable or unstable. So a little bit more information here. Nyquist plot is going to be a polar plot of the frequency response function of a linear system. What this means is that our Nyquist plot is going to plot the transfer function here with our g of s with s equal to j omega. That means that you want to plot g of j omega there, where this is going to be a complex number for any angular frequency or omega term here. So the plot is a plot of complex numbers. Now, this complex number is going to depend upon frequency, so frequency is going to be a parameter if you plot the imaginary part against the real part. So as we think about doing this plot out here, and we're going to sketch the polar plot of a frequency response here. So we're going to plot this, do a polar plot of our g of j omega. The entire range of the frequency from 0 to infinity, there's going to be 4 things that we really need to consider and make sure that we know in order to do this. So 1, the start of the plot where our omega is equal to 0. 2, the end of the plot where omega is equal to infinity. Then we're also going to need to know where the plot crosses the real axis and where the plot crosses the imaginary axis. Let's take a look at a really simple example here in this problem here. So in this sample problem number 1, we're looking at the polar plot of integrator here. So we're going to consider a very simple first order system here where our g of s is equal to 1 over s. Now, representing g of s in the frequency response form here, our g of our j omega here, and then replacing this with s is equal to j omega, well, we end up here, when we replace, okay, you can see our s is right here, replace that with our j omega right there, so we end up here with g of j omega is now equal to 1 over our j omega term, or our negative j over omega right here. So the magnitude of this is what we want to calculate next here. So we take the magnitude of this here, we do that, and this ends up being a 1 over omega. So the phase now, because we want magnitude and phase separately, the phase of this is going to be denoted by our phi right here, and this is obtained as the angle here of our j omega, which is going to be, in this case here, negative 90. So we can take a look down at our Bode plot versus our polar plot for this here. And again, remember, if we're dealing with our Bode plot, we're looking at our magnitude and our phase separately here. So we have a separate plot for each of those. So we can have our phase versus angle here, our magnitude right here in dB on our y-axis for both of those there. See our Bode plot as we vary our omega there from 0.1 to 10 on this log-based plot here, and the same x-axis on this one here, and we're looking at our phase. So we're comparing those two right above and below each other for phase and magnitude on each a separate plot when we're dealing with our Bode plot. But now if we're dealing with our polar plot over here, then you can see they're both going to be on the same axes here. So I'm going to talk briefly here about the design approach with the Bode plot. So there's classical methods on the Bode plot, obviously have a large component of trial and error. So we can see just from our technique right there, you're going to be trying one thing, it doesn't quite work, try something else. And this is due to the fact that the phase and the gain curves must be manipulated in order to achieve the acceptable design. So it's a lot of back and forth and trial and error with that there. So if you're given a set of specifications and a couple different engineers are working on it at the same time and use methods, they're going to arrive at different designs at the end. Because again, it's that trial and error back and forth, and it's user interpretive. So an experienced designer, however, can often obtain a good design quickly with these techniques. And that's just due to the fact that he's done a lot of these. He knows what works, what doesn't work, rough ideas where to start, things like that he can put in. But it's really a skilled trade that you need to be able to have just a lot of experience in order to quickly get a good design result. So this is where, if there's a lot of back and forth and trial and error testing with this, using a computer plotting routine is going to speed up this process. You can write in a couple of loops, a couple of algorithms here to quickly check and back and forth and plug new things in to see what works. So it's going to be difficult to state a rigid set of rules to follow for designing this because it is up to a skilled designer in order to do this. And even when you're talking about computer plotting, where the skill comes in is how you write that algorithm, where you start, where you end, how many iterations you're going to be doing. So those are all things to keep in mind whether you're doing a design approach using this Bode plot. Now, with that being said, with a lot of these skilled designers, they've kind of come up with a few rough criteria or guidelines that might be good to follow here. So we call this our design approach right here. So if we want to minimize our steady state error, the open loop gain should be kept as high as possible in the low frequency range of the Bode plot. So again, these are just kind of general rules of thumb from these designers who have done this over and over again that'll give us a good starting place to jump off as we're doing our design. Now, at intermediate frequencies or near the crossover gain frequency, a slope of negative 20 dB per decade in the gain curve will help to provide an adequate phase margin there. So there's another thing here. If we're looking for that phase margin, try to get that just about right. There's a little tip right there. Now we'll go to the higher frequencies. A small gain is going to be desirable to obtain high frequency disturbances such as electronic noise, mechanical vibrations induced by gear teeth, shafts, all the disturbances that we talked about before at the beginning of this. Those are things to consider now as we're talking about our high frequencies and utilizing a small gain. So next, I want to go through an example problem here. And a part of the reason I want to go through this is to give us just a simplistic example problem for designing a compensator so that we have a problem that we can reference back to as you're taking a look through some of the examples in the textbook, or if you're doing through some of your homework problems as well. We want to have a basic guidelines. Now, the response I got from students and feedback I got was a lot of times with these problems, they have a difficult time knowing where to start. So I figured a couple simple example problems for you guys to reference back to might give you some ideas on how to get started on these different design problems here. So for this problem here, we're also going to be taking a look at utilizing MATLAB to do out some of these plots. So we talked about earlier in the lecture how using some of these computer systems for this trial and error and back and forth, and we're constantly changing things to optimize the system to meet the specifications and requirements, is going to be a lot of that back and forth and trial and error. So writing a program with a for loop or an algorithm that'll help us do that is going to be very important. So going back to this problem here, they asked us to design a lag compensator so that our ramp error is given to us here, the coefficient is given to us here. They give us our gain margin as well as our phase margin. So we have our gain margin here of 20 dB, and we have our phase margin of at least 45. And they also tell us to assume that the compensator's phase angle is 5 degrees. Now they also give us this diagram here for our system right here. So we can see we have our input and our output here. We have our feedback loop coming down through here. We have our G sub C function here, and we have this function here of our K over our S times S plus 5 times S plus 20 there. Now from that information up here, what we can do is then develop our open loop transfer function. So we can see the denominator of our open loop transfer function right here. We have our S right there, times our S plus 1, our S plus 1 there, our S plus 5, our S plus 5, and our S plus 20 from our S plus 20 there. And on our numerator here, we have our 2kg, so there's our 2, our G sub C, and our K function there. So this is our open loop transfer function there from our given diagram there. Now we want to consider the case where G sub C of S is 1 and K is 50. So for this here, we're also going to now replace our S with our J omega. So from that, we now get this down here in this form here. Our G of our J omega, once we sub that in there, is equal to 2 times our 50 right there that we can plug in as our numerator. And we can see where that comes from. We have our 2k G sub C, where our K is 50. Our G sub C is only 1, and there's our 2 value right there. So this comes right in here. This is our 2 times 50 on the top, so it's going to be 100 on the numerator right there. All divided by, now we have our 5 times our 20 right there from our given information, our problem statement, times our J omega, times J omega plus 1, times our J omega over 5 plus 1, times J omega over 20 plus 1, which we can rearrange and simplify this down. And what we end up with here, we can see a couple things are going to cancel on the top and bottom, so that's going to go away. That's going to cancel with that. It's going to leave us a 1 in our numerator up there, times our J omega times J omega plus 1, times J omega over 5 plus 1, times our J omega over 20 plus 1. Now from here, we can get this into the form here, which takes 20 times the log of this function over here now when we go through this with our magnitude there. And what we end up with this relationship here is the ability now to create a MATLAB code. So even with a simplistic problem, we can see that this could be a little bit tricky to do out by hand and be rather intensive, especially if there's going to be a lot of back and forth and trial and error. So then what we can do is we can create MATLAB code for this bode plot. Now I've written it out here. It'll be in the PDF of the PowerPoint of my lectures as well, but I'll also include my script file for this so you guys can reference back to this and tweak this, play around with it within MATLAB on your own. So this will be uploaded to Blackboard as well as a script file along with what you see here. So we can see we go through, we can define all of our values here. at the top within our MATLAB code, and we're calling out a subplot. So again, we want our phase and our magnitude on the same plot right here. So again, this is kind of the old school way of doing this. There are new functions within MATLAB that we can utilize that are 1 or 2 lines and not all of this. But I go through just to kind of show you how we can tweak our labels, we can tweak our values for our limits here, title the plot, all this information we can do right within MATLAB. So then we could quickly go back and we could change things. So if we wanted to modify something in here, we could go back and quickly change one line of it, or we could even include this within a loop and say, okay, we want to alternate this from 1 to whatever it might be for our values, plug it in and have it keep spitting out plots so we can compare them and look at them. So once we plug that into MATLAB and rub that script right there, we get these plots out here. So again, with our Bode plot, we recall we separate out our magnitude and our phase. They're 2 separate plots here with our Bode plots here. So on the top, we're going to look at our magnitude here, and on our y-axis we have our magnitude in dB. On our x-axis we have our frequency in radians per second, and that's the same for our phase angle plot down there. So we do this here, we can take a look, we plot this out, and what we can do is from our intersects on this here, we can then get some information. We can get our GM, gain margin, we can get our PM, our phase margin right there. So we get that information by doing these intersects here. So if we're looking at our gain margin, we can say, okay, I can take this intersect here. I can draw a line straight up from my phase angle up here, see where it intersects my curve here on my magnitude plot here, come over here and get my magnitude value right here. So my GM, if I look at that, ends up being 13 dB. I can do the same thing here, or I can say, okay, these two intersect right here. So now I can draw my line straight down here, and I can come over here where it intersects and come over here and get my phase angle in degrees there. Convert it to the right coordinate system if you're only dealing with positive rather than negative. Make sure you pay attention so we can get that value there. And on these 2 lines that we draw from one of the others intersect, this is our omega G and our omega P right there. So all that information is gathered from these plots. Now this again was doing it kind of an older way where I didn't draw those lines in. I did this just within PowerPoint here and put those lines in and just interpolated off of these graphs in order to get that. I could also, within MATLAB on these plots here, open up the plot there, and I can click on each of these within MATLAB, and it'll tell me what that point of intersection is, and get my values that way from MATLAB. Now also there is some more commands you could do within this, within the plotting, where we could draw these lines in and plot them at the intersects if we wanted to take the time to do that, or we could use some of the new functions within MATLAB that I'll include some links to that automatically put these in with your Bode plots.